In this session, we'll explore critical machine learning models and concepts, including distance-based models, naive-Bayes classification, support vector machines, that is SVM, and your principal component analysis, PCA. We'll also discuss their applications with step-by-step examples. Distance-based models. So what are they? They are models that classify or predict data points by calculating their similarity or dissimilarity using a distance metric. These models rely on proximity between data points in a feature space to make predictions. Now, a few key components of distance-based models can be distance metric, where it is a mathematical formula to compute the distance between 2 points in a data set, and this is a common metric including Euclidean, Manhattan and Hamming distance. Second is in neighbors. Data points closest to the query point are considered its neighbors. And thirdly is a decision boundary, which is a line or surface separating different classes based on different calculations. Now, few different types of distance-based models can be the KNN, which is the K nearest neighbors, and K means clustering, or distance weighted models. In this, we'll be learning about the K nearest neighbor classification in detail. It's based on distance-based models. One is image recognition or image classification, where we recognize objects in images. In this, we use KNN to compare feature vectors of images with label data. An example being, you can identify whether an image is a car or a human being or a cat. Then you have recommender systems, which is used to recommend items based on user preferences. For example, you can suggest movies based on the preference of similar users using consign similarity. Then you also have medical diagnosis or anomaly detection, where we predict disease based on symptoms. Here we identify whether a patient has diabetes based on test results. In this case, we compare a patient's features, that is, we compare the age, blood pressure, or various other factors with historical data using KNN. And we also have something called as market segmentation, where we group customers based on behaviors. And for example, we create targeted marketing campaigns for high spending customers. Which is K nearest neighbor classification, is a non-parametric instance-based learning algorithm which is used for classification and regression tasks. In classification, KNN assigns the class to a data point based on the majority class of its K nearest neighbors in the feature set. It is also called a lazy learner algorithm because there is no explicit training phase in this, and the computations are performed during the prediction. This is instance based, which is it relies on the entire training data set for making predictions. And why is it called a non-parametric algorithm is it does not make any assumptions on the underlying data. For example, KNN is used to classify between two different objects. Like suppose you have to classify between a dog, you have an image to classify between a dog and a cat. Now, but we don't know whether it is a dog or a cat. So for identification, we use this KNN algorithm. So how it works is basically it will find similar features of the new data set that is there and compare it with the cats and dogs images, and based on the similar features it will put on either the cat or the dog category. And in terms of graphs, now suppose we have two categories, which is the A and B. If a new data point is added, with the help of KNN, we based on the Euclidean distance, we classify it either under category A or category B, depend on how close it is to either one of them. KNN working can be explained based on algorithm which has 6 steps. First, we select the number of neighbors. Then we calculate the Euclidean distance of the k number of neighbors, and then we take the k nearest neighbors as per Euclidean distance, and then we among these k neighbors we count the number of data points and assign the new data points to that category for which the number of neighbors is maximum. We will see this in more detail. Now suppose we have a new data point and that we have to put it in a category. So the first step will be we have to choose the number of neighbors. We select the number of neighbors to consider during the classification. For this you can either start with k is equal to 3 or k is equal to 5. Now here we have question about what is the impact of k. Now if the k value is small, it can lead to overfitting, and if the k value is larger, it might smooth out the entire decision boundary, causing underfitting. So hence in general cases we'll choose k is equal to 5. Next step, we have to calculate the distance. We have to measure the distance between the query point and all the points in the training data set. Now the common distance metrics can be either the Euclidean distance, which is d is equal to under root of n whole thing xi into minus yi whole square, or you can have the Manhattan distance as well in this case, which is d is equal to n to the power xi minus yi absolute value. Next we'll have to identify the neighbors. Based on that, we saw the training data points based on the distances to the query point, and then we select the k nearest neighbors. Here in this case, as you see, the 3 nearest neighbors from category A, hence the new data point will be belong to category A. So then here we assign a class. So once we perform a majority vote among the k nearest neighbors, we assign the most common class to query point. Support vector machines, or SVM. It is a supervised learning algorithm that is used for classification and regression tasks. Now it aims to find the best decision boundary, that is a hyperplane that separates data points into distinct classes. Now the main purpose of SVM is to maximize the margin between data points of different classes, or ensuring better generalization to unseen data. Now let's say an example, we see a cat that has some features of a dog, and we want to see if the model can accurately identify that if it is a cat or a dog. Now that model has to be created using the SVM algorithm. Now what it does is, we train the model first with a lot of images, then we test it with a strange creature. With that we create a decision boundary based between these two data, and then we choose the extreme cases, and it will see if it is the extreme case on a dog or a cat. On the basis of the support vectors, it will classify it as a cat. The applications are generally used for face detection, image classification, and text categorization. Now, there's generally 5 types of SVM. One is linear SVM, which is used for linearly separable data. Non-linear SVM is used for non-linear separable data. Then you have your support vector regression, which is used for regression tasks, which is instead of classifying, it only predicts the continuous values. Then you have your multi-class SVM. It is used to target variables which has more than 2 classes. And then finally you have your structured SVM, where it extends the SVM to handle structured output spaces like sequence, trees, or graphs. Here we'll learn about the 2 linear and non-linear SVM in detail. Moving on. Hyperplane and support vectors in SVM. What is hyperplane? It is a decision boundary that separates data points into classes. Now in 2D space it's a line. Now in the case of a 3D, it can be a plane. In higher dimensions it is a hyperplane. Now the dimensions obviously depend on the features present in the data set, and we always create a hyperplane which will have the maximum margin, that is the maximum distance between data points. Support vectors, they are basically data points closest to the hyperplane, and these points are mainly what influence the position and orientation of the hyperplane. Now moving on, linear SVM. A formal definition of linear SVM is it is used for linearly separable data, where a straight hyperplane can divide the data points into two classes. Now how it works is basically it finds a straight line that maximizes the margin between two classes, or in case of high dimensions it can be a hyperplane, and it works the best when the data set has no overlap between these classes. Now like say for example, now you classifying email as spam or not spam based on the straightforward features like presence of certain keywords. Here as you see the graph for the SVM, linear SVM, which has been explained in detail. Moving on to non-linear SVM. Now non-linear SVM, the formal definitions, it is used for obviously non-linear separable data, unlike your linear SVM where in this case the classes cannot be exactly separated by a straight line. Now what it does is you have to apply something called as a kernel trick to map the data into a higher dimensional space where it becomes linearly separable. Here in this case, to separate the data points, we need to add one more dimension. In linear separable data, we can have two dimensions, that is x and y. Hence the equation for linear dimension is w into x plus y is equal to 0. Whereas in this case, since it cannot be separated by one particular straight line, we need to have one more dimension. So then the equation becomes z is equal to x square plus y square. The image also is as given by adding the third dimension. This way the SVM will divide the data sets into classes in the following way. Probably it is defines the probability of some event happening with respect to another event. That is, it is the probability that the likelihood of an event occurring given that another event has already occurred. Like for example, when what is the probability of playing tennis given that it is sunny? Or like say a doctor wants to know the probability of a patient that has a disease given that the patient has tested positive for that disease. Now the formula for such a case is P of A slash B is equal to P of A intersection B divided by probability of B, where P of AB is equal to probability of events A and B both happening. PA translates to probability of the event A to occur, where PB is equal to the probability of event B to occur. P of A slash B is the probability of event A happening when B event is already occurred, and P of B slash A is the opposite, which is the probability of event B happening with respect to event A when it has already occurred.